We have discussed so far general electromagnetic fields, introduced electromagnetic potentials with Coulomb and Lorentz gauge, and then we talked about waves, wave equation, and 1D example of a wave on a string, and then finally discussed reflection and transmission of waves on a string. With this background, we are now ready to discuss plane electromagnetic waves, their propagation and their reflection transmission across boundaries. So, today's lecture is going to be on general properties of plane electromagnetic waves. Recall that we had this wave equation for the electric field and magnetic field. One of the solutions it admits is E r t equals E 0 cosine of k dot r minus omega t plus some phase phi. That takes care of whether it is sine or cosine or something in between, and B r t equals B 0 cosine of k dot r minus omega t plus phi. Notice that the wave is traveling in the k direction, number 1, and number 2, its amplitude is constant. Without any loss of generality, I can take k to be equals k z, that is the propagation direction is z. So, that I do not have to write the vector sign all the time, and then I am going to write E as a function of z and t as E 0 vector cosine of k z minus omega t plus phi, and B z t equals B 0 cosine of k z minus omega t plus phi, and again E and B are functions of z and t only, they do not depend on x and y. So, what is happening is that this wave is traveling in the z direction and there is no dependence of E and B amplitudes on the x and y direction. So, they are constants over this x and y plane. All right. So, now we will see that from Maxwell's equations what are the further conditions on E and B. So, remember what I said right in the beginning of this week is that if I satisfy the wave equation, it does not mean that E and B are the solutions of the electromagnetic waves. That is because they still have to satisfy the Maxwell's equations individually. Now, before I do that, let me switch to complex notation, which is very convenient while dealing with waves. I do not really have to worry about the trigonometric identities at that time. So, I am going to first introduce that complex notation. So, what I have is E as a function of z and t as E 0 cosine of k z minus omega t plus phi, and same thing with B, E 0 is a vector. So, I am going to write this as real part of E 0 vector e raised to I k z minus omega t plus phi. I can further absorb phi or e raised to I phi with E 0 and write E z t equals real part of E 0 e raised to I k z minus omega t. and then it is understood that E 0 is complex because it has that e raised to I phi. So, now once I introduce that, I have to really work out how different quantities are calculated. So, first let me write B also B z t equals real part of B 0, which is understood to be complex I k z minus omega t. Now, so we are saying that the wave equation admits these solutions. However, they are not complete solutions until I really specify what B naught and E naught are and what conditions do they satisfy. Now, I am going to drop real, writing this all the time, and finally, we understand that finally, I have to take real part of this whole thing. So, now let us see, again going back to general notation, I will write E r t equals E 0 understood to be complex e raised to I k dot r minus omega t, and B r t equals B 0 e raised to I k dot r minus omega t. There are no sources, and therefore, what I have is that divergence of E is 0, and this immediately implies, and you see now the advantage of using this complex notation is that it gives you I k dot E 0 e raised to I k dot r minus omega t equals 0. And this means for all the time this has to be satisfied that k dot E 0 is 0. This comes from the Maxwell's equations. You see, the wave equation gave me a solution, but now I have to put these further conditions. All 4 Maxwell's equations have to be satisfied, and that immediately puts a restriction that E 0, the amplitude is perpendicular to the propagation direction. That is number 1, and underline this statement. Next, we see that divergence of B is also equal to 0, and this immediately implies k dot B 0 is 0. So, B 0 is also perpendicular to the propagation direction. Second Maxwell's equation satisfied. You may have done all this, but I am just repeating it for completeness. Third, I have curl of E equals minus dB dt. And again, since I am using the complex notation, life becomes quite easy. You see, E r t is E 0 e raised to I k dot r minus omega t, and B r t is B 0 e raised to I k dot r minus omega t. So, taking curl basically means that I cross with k. So, I k E 0 e raised to I k dot r minus omega t is common. So, that will cancel from both sides, and on the right hand side I am going to get minus I omega B 0. I cancels, and I get B 0 vector equals minus k vector over omega E 0. K is the propagation direction, and mod k over omega is 1 over c. So, it comes out to be 1 over c propagation direction unit vector cross E 0 with a minus sign. So, this tells you that B 0 is perpendicular to E 0, such that the propagation direction times E 0 with a minus sign in front gives you the B 0 direction. Similarly, I get from the last equation curl of B equals 1 over C square d E dt. The same thing I get I k cross B 0 equals 1 over C square I omega E 0. This is with a minus sign, so I made a mistake in the beginning. Let me correct that mistake. This mistake was this minus sign. I should remove this because this was with a minus sign in front. So, this guy goes away, this guy goes away. So, you get this I cancels and you get mod k over omega cross B 0 equals minus 1 over C square E 0, which is basically the same as this. So, let us see what is the implication of all this. I will make a picture in the next slide. So, suppose this is k direction of propagation, then E has to be perpendicular to it. So, this is let us say E. So, I have drawn this plane of the screen to be E k plane, and then I have B equals k cross E. So, B would be coming out. If you work out those equations, you will also see that E cross B gives you the direction of propagation. So, I leave this for you from the equations that B 0 is equal to 1 over C k unit vector cross E 0 show that E 0 cross B 0 direction is the direction of propagation. So, we found this, that the wave equation del square E minus 1 over C square d 2 E by dt square equals 0 and del square B minus 1 over C square d 2 B over dt square equals 0 admits solutions which are of the form E R t equals E 0, which is understood to be complex e raised to I k dot r minus omega t, and same thing for B R t equals B 0 e raised to I k dot r minus omega t, and k dot E 0 is 0, k dot B 0 is 0, modulus of B is 1 over C modulus of E, and E naught cross B naught is the direction of propagation, and so on. So, E, B and K form a triad. So, let us say if we have a wave going in the z direction, if I have a wave going in the z direction, this is x, this is y, then I will have E in the x direction, B in the y direction, and this is the direction of propagation z, k, and various combinations of this. It is understood when I write the electric field E as some E 0 e raised to I k dot r minus omega t, that E 0 is complex, and in fact, it will be E 0 modulus e raised to I phi, where phi is the phase, right, and mod E 0 then is the amplitude, and phi gives you the phase, right. And now, finally, when I look at E in space or B in space, the real part of E R T or B R T is to be taken. So, this is how we are going to describe the amplitude, the phase and everything for a plane wave. I would also like you to, just for practice, derive all the results that we have obtained so far using real representation, that is taking E R T to be E 0 real cosine k dot r minus omega t plus phi, and similarly for B. Now, let us see, when I have these equations, what about the energy, intensity and momentum of plane electromagnetic waves, and I want to also use the complex notation, because as I just said, it makes life easy, and you will see when you do the problem that I have just given you, that in the case of real quantities, you have to play around with trigonometric identities. So, let us first do the energy density in plane EM wave. So, I am talking about E R T, which is taken to be E 0 e raised to I k dot r minus omega t. Let me write this as E 0 r e raised to minus I omega t. I am doing this so that I can separate out this time dependent part over which I am going to take the average. So, E that is observed is given by real part of this. So, real of E R T is going to be equal to 1/2 of E 0 r e raised to minus I omega t plus E 0 r star e raised to I omega t. So, the energy density is going to be equal to 1/2 epsilon 0 real E R T square, and I will indicate by this angular bracket is time averaged. Where time average means I am taking 1 over t dt 0 to t. Now, real t, real E R T is equal to square is equal to 1/4 of, you multiply, you are going to get E 0 r square e raised to minus 2 I omega t plus E 0 star r square e raised to 2 I omega t plus 2 E 0 r star, that is it. And time averaged of e raised to 2 I omega t same as 1 over t, 1 over t e raised to minus 2 I omega t dt, which is 0. And therefore, when I take the time average of this quantity, real E R T square, this comes out to be 1/2 E 0 r E 0 star r. Notice that when I take E 0 r and E 0 star r, the e raised to I k dot r term cancels out, and so does the e raised to I phi. See, E 0 r times E 0 star r the dot product, this is a dot product, this is a dot product, is equal to the amplitude mod E 0 square, because e raised to I delta, e raised to I k dot r cancel out. So, we are getting it all right, and therefore, energy density due to electric field is 1/2 epsilon 0 the time averaged of real E 0 r square is equal to 1/2 epsilon 0 times 1/4 times 2 E 0 r dot E 0 star r, which comes out to be equal to 1/4 E 0 r dot E 0 r star. Similarly, in exactly the same manner, there will be energy density due to the magnetic field, or there is an epsilon 0 also here, which will be 1/4 mu 0 B 0 r dot B 0 r star, which I can write as 1/4 mu 0 c square E 0 r dot E 0 r star, which is epsilon 0 over 2 E 0 r dot E 0 r star. Therefore, the total energy, this is 4, the energy density in a plane EM wave is equal to, adding the two, 1/2 epsilon 0 E 0 dot E 0 star. I am dropping that r, it is understood, it is there. So, we found the energy density. So, if I were to make a picture, here is this electromagnetic wave propagating in this direction. It has this E field, it has this B field, and is propagating forward, right. So, at certain instant, if I were to take a snapshot, it will look like this. And B would look like this, and is going in this direction. The time average energy, if I were to plot energy content, so energy density, which I will call U small electromagnetic time averaged as a constant, and it is equal to 1/2 epsilon 0 E 0 dot E 0 star, and in terms of real quantities, this can also be written equal to 1/2 epsilon 0 mod E 0 square, that is the amplitude of the electric field square. The complex notation is for mathematical convenience, otherwise you can just write as amplitude square 1/2 epsilon 0. Equal contributions to the energy coming from the magnetic and the electric part. So, if I were to plot this again, I will have the magnetic part, the electric part, both time average are 1/4 epsilon 0 mod E 0 square. Magnetic part is 1/4 epsilon 0 mod E 0 square, and the total is then 1/2 epsilon 0 mod E 0 square. This is U E M. So, this is the energy. Now, as the wave propagates, it also carries energy, and we know what it is given by. This is given by the Poynting vector. So, Poynting vector S we had calculated as 1 over mu 0 E cross B. What we need to calculate now is the time averaged S. Why? Because if I take this wave which is propagating and I consider a plane perpendicular to it, right, over here the field oscillates like 10 raised to 14 to 10 raised to 15 per second. We can't really see the variation. All we can talk about is the time average quantity. Just like the energy coming from the sun, you see it coming to you continuously, because the electric field is oscillating with that high frequency. So, we need to calculate time averaged S. Okay. So, let us do that. So, let us write S, which is 1 over mu 0 E cross B, which is going to be equal to 1 over mu 0 times 1/2 E 0 R e raised to minus I omega t plus complex conjugate E 0 star R e raised to minus I omega t crossed with 1/2 B 0 R e raised to minus I omega t plus B 0 star R e raised to, this should be plus I omega t. And this comes out to be 1 over 4 mu 0, and you go inside, you get E naught R cross B naught R e raised to minus I 2 omega t plus E naught R cross B naught R starred e raised to plus I 2 omega t, and then you have plus E naught R star cross B naught R plus E naught R cross B naught star R. When I take the time averaged quantity, so if I calculate S, it will come out to be, the first two terms give you 0 and the last two terms give you equal contribution. So, it comes out to be 1 over 2 mu 0 E 0 cross B 0 star. Again, because we are taking star, all the quantities, the phase factor, they cancel out, and this will come out to be 1 over 2 mu 0 amplitude E, amplitude B in the k direction. Amplitude of B is E naught by C. So, I can write this as equal to 1 over 2 mu 0 mod E naught square over C. And if I multiply this by epsilon 0 over epsilon 0, I get this equal to 1 over 2 mu 0 epsilon 0 C times epsilon 0 mod E 0 square, which is C times 1/2 epsilon 0 mod E 0 square, which is C times U E m time averaged in the k direction. So, I should not be forgetting that. All this is in the k direction. So, what you have is that this wave is filling all the space with certain energy density and is propagating in this direction. with speed c. The energy density all over this is u E m. So, per unit time how much energy is going to flow, and you can see the per unit time energy flow is going to be c u m u E m. Very easy to remember, just like a fluid flowing, right. So, just to draw an analogy, if in a pipe you have fluid of density rho flowing with the speed v, per unit area the fluid that flows is rho v. In exactly the same manner, so all over the space I have u E m energy density and it's flowing with speed c. So, per unit area energy flow is going to be c times u E m. So, that is the Poynting vector S time averaged is c time average u E m in the direction of propagation. Does it carry momentum? Right. So, does the E m wave carry momentum? Yes, it does. Whenever there is an S, there is a momentum, and we had already learned that momentum density is S over c square, and time average will be time average S over c square. And therefore, you have momentum density in the plane electromagnetic wave as u E m over c, and its direction is k. So, if there is this electromagnetic wave filling the space, just like it contains energy per unit volume u E m. So, if I take a volume v, the energy in this is u E m time average times v. The momentum contained in this, is going to be u E m by c times v. That is the momentum contained, and it momentum also has a direction. So, it will be in the direction of k. Obviously, if there is momentum, just like there is energy flow, there is momentum flow also. What will be momentum flow? Momentum flow per unit area per unit time is going to be equal to c times momentum density. So, this is going to be equal to average u E m in the k direction. So, when there is this electromagnetic wave going in direction k, it is also carrying with it momentum p per unit area per unit time equals u E m time averaged k. It is also carrying with it energy per unit time per unit area equals c times u E m k. So, if I put a area in front of this wave coming in, this area is going to receive momentum and is going to receive energy. Energy heats it up, momentum gives it pressure. How much will be the radiation pressure? It will be momentum coming in. So, let us see if there is momentum coming in, P per unit area per unit time, and goes out, let us say P prime. Some gets absorbed and some gets reflected. Then the pressure is going to be equal to P times 1 plus reflectance, where R is the reflectance. This is quite remarkable that a radiation falling on something can apply pressure on it, and this was first demonstrated in 1901 in a paper by P. N. Lebedev in Annals der Physik, volume 6, page 433, 1901. It was also followed by another paper by Nichols and Hull in 1903, and this is in Physrev, volume 17, page 26, 1903. They demonstrated that radiation indeed applies pressure. Finally, on plane waves, I am going to talk about polarization of plane waves. So, in general, if there is a wave going, we had said that there is this E field. There could be E field perpendicular in the x direction and in the y direction, and they could have phases. Correspondingly, there will be a B field also, which will remain perpendicular to the E field at a given time, right. So, in general, I can write the E field as equal to E 1, I am just writing the amplitude, in the x direction e raised to I k dot r, I will again for simplicity write it as k z minus omega t plus some phi 1, right. So, this k direction I am taking to be same as the z direction, plus E 2 y e raised to I k z minus omega t plus phi 2. So, these are two phases. They could be time dependent in general, but right now I am taking them to be constant. Now, depending on what the relative phases are, the polarization of the wave could be linear or circular, left circular or right circular, and if the amplitudes are not equal, it could be elliptically polarized. And if phi 1 and phi 2 are time dependent and varying arbitrarily, it will be unpolarized. Now, as I remarked earlier, the field change at a rate of 10 raised to 14 to 10 raised to 15 per second. So, if I look at this field, I cannot really make out what the polarization is. You need to have some other techniques, right, and this is done by using Stokes parameters. So, what is done is take a series of filters, right, which something that would give you a linearly polarized light in one direction, other one which would give you at 45 degrees, something that is a quarter wave plate and so on, and you measure intensities after each of one of these, and these could be related to Stokes parameters. The Stokes parameters are defined as S naught, which is equal to x dot E square plus y dot E square, which is basically the sum of the amplitudes in the two directions, E 1 square plus E 2 square. S 1, by using filters and so on, right, and measuring appropriate intensities, is the difference between the two intensities. So, x dot E square minus y dot E square, which is equal to E 1 square minus E 2 square. So, with these two I can determine the amplitude corresponding to the amplitude in one direction and amplitude in the other. I am yet to find the phase difference, relative phase phi 1, phi 2, phi 1 minus phi 2, that will give me whether it is circularly polarized, elliptically polarized and so on. And for that, you again measure something called the S 2, which is nothing but 2 times the real part of x dot E star times y dot E, which comes out to be 2 E 1 E 2 cosine of phi 1 minus phi 2, and S 3 is equal to 2 imaginary part of x dot E star y dot E, which comes out to be 2 E 1 E 2 sine of phi 2 minus phi 1. So, by measuring these S naught, S 1, S 2, S 3, you actually determine all the amplitudes and their relative phases, and these are measured using different kinds of filters in series. But this is all I am going to talk about Stokes parameters. The only thing I wish to mention is that all 4 of them are not independent, right. So, what we have done is define Stokes parameters S 0, S 1, S 2 and S 3. This is E 1 square plus E 2 square, E 1 square minus E 2 square. This is 2 E 1 E 2 cosine phi 1 minus phi 2, 2 E 1 E 2 sine of phi 1 minus phi 2, and you have S naught square equals S 1 square plus S 2 square plus S 3 square. This is something which is satisfied. So, sometimes you also represent the polarization of something called the Poincare sphere, which is nothing but a sphere of radius S 0 and S 1 on one direction, S 2 in the other, S 3 in the third direction, and every point on this sphere represents a different state of polarization. So, this is a representation of Stokes parameters on Poincare sphere. So, to conclude this lecture, it is more of a kind of review of your whatever you have learnt in your BSc and MSc, is that plane EM waves described, use of complex notation which simplifies mathematical manipulations. Then we talked about the intensity, which is related to S, and radiation pressure, which is related to momentum density times C, and finally, polarization and Stokes parameters. Thank you.